Hello! Today we're going to derive Gauss's law for electric fields by scratch using the inverse square law. So let's take a random vector field that satisfies the inverse square law, which is 1 over r squared. It's in the r direction, so we have our unit vector e hat r, which is equal to your r vector divided by its magnitude. R itself is simply the square root of x squared plus y squared plus z squared. We can also write it in a different notation, I xi squared, where you sum the I, okay, where summation is assumed. So let's take the divergence of this vector field. Okay, so we take the dot product with the del operator and the vector field, okay? This is equal to e hat x, then we have the derivative with respect to x, plus e hat y, derivative with respect to y, and then e hat z, derivative with z, and then that's multiplied or dotted with r over r cubed, which is the same as saying 1 over r squared. Okay, so expand this and we get the derivative, the partial derivative of x over r cubed with respect to x, plus the partial derivative with respect to y of y over r cubed, and then finally the derivative with respect to z of z over r cubed, like so. Okay? So what we're going to do now is simplify things by saying x is x1, y is x2, and z is x3. This will allow us to simplify it by using summation. Okay? So therefore what we can write is the sum of I, okay? We have the partial derivative with respect to xi of xi over r cubed. That's what we're doing, isn't it? Here we've just simplified it to this. So we can use the chain rule. These are two different variables, therefore we take the partial derivative of xi with respect to xi, leaving r cubed constant. So we get partial derivative of xi with respect to x divided by r cubed plus xi, but this time we take the partial derivative of 1 over r cubed with respect to xi. 1 over r cubed, like so. Okay? Excellent. So, let's just break this down first. Let's look at this term, the partial derivative of xi with respect to x. Now, we can use the Kronecker delta symbol. Okay, it's equal to delta ij. What that means is if the i's are the same, so we get dx divided by dx, that's 1. If I and j are different, that should be j there. If I and j are different, so like the partial derivative of y with respect to x, that's of course 0. Okay, you're probably familiar with that already. Okay, so what is this then? xi, take the partial derivative with respect to x. Well, we can sum, of course, all our dimensions. We have I goes from 1 to 3, okay, x, y, and z, of the partial derivative of I with respect to x, xi, and that's just the sum of I equaling 1 to 3 of delta ij. That is simply 1 plus 1 plus 1, which is 3. So this partial derivative here is 3, so we get 3 over r cubed. Okay? Now, what about this derivative? We've got this, now let's look at this term. The derivative of 1 over r cubed with respect to x. Okay, so just to reiterate, we've got 3 over r cubed. Now we need to look at this partial derivative. So, the partial derivative with respect to xi of 1 over r cubed is equal to the partial derivative with respect to x of r to the negative 3, isn't it? Okay, that should be xi. This then is simple. It's just negative 3 r to the power negative 4, and then use the chain rule, so it's the partial derivative of r with respect to xi. Okay? Good. So, now I need to find the partial derivative of r with respect to xi. Okay? It's very simple calculus. That's just d by dx of the square root of x squared plus y squared plus z squared, like so. That's equal to a half square root of x squared plus y squared plus z squared, like so, to the power negative a half. Okay, and then that's multiplied by the partial derivative with respect to x of the inside, which is just x squared plus y squared plus z squared. Partial derivative with respect to x is just 2x, and therefore all of this becomes, simplifies to, that becomes 2x differentiate, and we get 2x divided by 2r. Okay, x over r. Okay, simple. So therefore, overall we get negative 3r to the power negative 4 of dr divided by dxi, which is equal to negative 3 multiplied by 1 over 1 to the power 4 multiplied by xi divided by r. Okay, so finally we get that the divergence of a vector field that satisfies the inverse square law is equal to 3 divided by r cubed minus 3 divided by r cubed, which is 0. Okay, that's because we have this, that was equal to 3 over r cubed, and we can rearrange. Well, first of all we calculated the partial derivative, that gave us negative 3 over r to the power 4 times xi squared divided by r. We can rearrange that to give you negative 3 over r cubed. So therefore we get our result. The divergence of r over r cubed is equal to 0 if r is not equal to 0. Okay, so now we can use the divergence theorem. If you're not familiar with the divergence theorem, then go and watch my videos. But anyway, if we take the integral over our volume V of the divergence with respect to infinitesimal volume, that's equal to the integral of r over r cubed dotted with dA. Okay, so if we take a sphere, for instance, that's what we're working on. Okay, and we have a small radius, we call it capital R. Okay, on the surface, it's a tiny surface dA, or the vector dA is equal to dA multiplied by our unit vector. That's perpendicular to the surface. Okay, so we can rewrite it like this. Okay. Good. So, therefore we can rewrite the divergence theorem as the integral over the closed loop of r, which is just fixed now, it's just a fixed radius, divided by r cubed dA. Okay, that's equal to 1 over r squared. Okay, and then we have the integral of dA, like so. So that's very simple. We just find the total surface area of our sphere, and that becomes 4 pi r squared divided by r squared, which is equal to 4 pi. Okay? So using divergence theorem, we got 4 pi. So let's rewrite this in total. Okay, so the volume integral V of divergence of r over r cubed dv is equal to 4 pi. So you might be able to see where we're going with this, but let's just carry on. Now we can divide by 4 pi, can't we? If we do that, we get the integral of the divergence, as usual. And then we have 1 over 4 pi, and then our unit vector divided by r squared. And then that's multiplied by d cubed x, and that is equal to 1. So doesn't this look familiar? 1 over 4 pi r squared, maybe? Now we can use the delta function, okay? If we take the integral from negative infinity of the delta function with respect to x is equal to 1, where the delta function is 0 if x is not equal to 0. Now, go back to our divergence theorem, and therefore we can write that the divergence of our vector, which was 1 over 4 pi e hat r divided by r squared, well, that's simply the delta function in 3 dimensions, isn't it? Okay, it acts exactly the same way as the delta function does under the integral. Okay, now let's quickly look at Coulomb's law. Okay, the force F is equal to 1 over 4 pi epsilon naught, and then our unit vector divided by r squared, multiplied by the product of our two charges. Okay, so we take the test charge, little q, and we multiply that by the electric field strength is equal to the force. Okay, so E is equal to 1 over 4 pi epsilon naught E hat r divided by r squared q. Okay, now let's go back to our divergence. Therefore, what we can do is we have the divergence of E is equal to our delta function multiplied by q over epsilon naught. Okay? Our delta function was given by this, therefore that's what we get for our divergence theorem for the electric field. Okay, so as we established, the integral from negative infinity to infinity of the delta function with respect to x is 1. Now if we take some function f of x and we put that into the equation, we get f evaluated at 0. Okay, we can do a similar thing with y minus x. Instead, it's f of y. Okay, so therefore, in terms of the three-dimensional delta function, we get f of the vector y. Okay, so let's go back to the charges we were dealing with. We can therefore write d3x, that's just in 3 dimensions, and then we multiply that by a charge distribution rho. Okay, like so, just put that in the equation we had, and we get the charge distribution evaluated at y. Okay, so simply using the equation we had before, we can therefore write the divergence of the electric field. Okay, it was the delta function before of times q divided by epsilon naught. Using this equation, it therefore becomes, very simply, the charge distribution, okay, of x divided by epsilon naught. You may know this as Gauss's law. We can write it in a slightly different way. Instead, we can use the integral dotted with E. Okay, and then we have our small volume, and that's equal to Q over epsilon naught. Okay, so if we sum all the charge, it's a charge distribution. If we sum all the charge densities, we get the overall charge. Okay, and that is Gauss's law for electric fields, derived from scratch simply by looking at a vector field that satisfied the inverse square law and knowing a couple of calculus tricks along the way and Coulomb's law for charges. I hope that helped, and I'll see you in the next video.